Okay, good morning, everyone. Today we're going to be carrying on our exploration of simple population models in discrete time. And the other day we looked at the logistic growth model and we did some cobwebbing, a geometric technique to analyze that model. And we saw that as we increase the intrinsic growth rate of the population, that things started to get a little bit crazy around our carrying capacity. So we're going to be talking today about why that happens due to things called bifurcations, and bifurcations more generally will be meeting throughout this course, and the concept of chaos. So you should be able to understand what is a bifurcation point by the end of the day. What are a couple of types of bifurcation that we've met in this model and in other models, period doubling and transcritical bifurcations, and then what it means when we say that something is chaotic. We'll also be able to plot and interpret bifurcation diagrams by the end of today. So like I said, last time we looked at cobweb diagrams in our logistic growth model, and we saw that the behavior started to change as we increased R. And we saw something like this. So we were plotting cobweb diagrams like on this right-hand side. And so when R was less than 1, we had a picture that looked like this. And if we step up using this, following this green trajectory here, we end up tending towards our carrying capacity monotonically. So this was an example of something that is monotonically stable. This point here. Then as we increase R, what we're doing is we're changing the gradient. We're pulling this peak. On the top one, we can't really see it, the peak's actually over to the right-hand side, below that red diagonal line. Here, we're pulling the peak over this side, which means we're now going down. In this case here, our gradient is negative, but it's less than 1. So now, rather than tending towards it monotonically, we tend towards it, but oscillate around it. So if we've got time series of these, so on the left-hand side, we've got time series graphs on the top, we just tend to it from one side, the carrying capacity. Here, we're going to overshoot, undershoot, overshoot, and so on. But over the long term, we're going to tend towards it. So these are also called damped oscillations. So this point here is oscillatory stable. We found that if you keep increasing R, though, to the point where the gradient of that intercept is at magnitude greater than 1, but is steeper than -1, so steeply negative, we ended up seeing that this point here becomes oscillatory unstable. But precisely what the dynamics look like depend very finely on what that gradient is. So both of these cases, it's oscillatory unstable. In the top case, it kind of looks sort of stable, right, in the sense that it's just going back and forth between two values. This is known as a 2-cycle. Okay, so we approach it and then we just oscillate around it. We're still undershooting and overshooting, but we're neither moving away from it nor moving towards it. Okay, so we're just oscillating back and forth between these two different values. If we keep going, we should find that this breaks into a 4-cycle. So we're going between 4 different values, and then 8 different values, 16 different values. And then eventually we end up with something that looks like this. And this is chaos. So we're doing exactly the same process as we did before. We've just increased the negativity of this slope here at this intercept. As we do that, we still follow our cobwebbing trajectory, but it takes us all over the place. And then when we plot a time series, it looks something like this. So why does this matter? Well, there are a few reasons. One of the reasons is that if you were to go out and look at data like this, it kind of looks random, right? It's going up and then down and then down. Sometimes it goes up, and then down, or down, down, and up. But it kind of looks like it's going all over the place. It doesn't look like there's any sort of like predictability going on here. So in this and other models, we can summarize how the steady states of our model change, how the stability changes, using a bifurcation diagram. Okay, so what we're doing in a bifurcation diagram is we'll have our steady states on the vertical axis, and then on the horizontal axis, we'll have a parameter, a bifurcation parameter, it's called. Just a parameter in the model that as we vary, something happens to our steady states. We can do this numerically, and we can also do this by sketches, and they can look a little bit different when we do them in those two different ways. This is an example of the bifurcation diagram that we get from the logistic growth model. So like I said, we've got our population size here. I've scaled it, so it's relative to our carrying capacity K. And here's our intrinsic growth rate R varying along horizontal axis. So what's going on here? Well, as we increase this value of R, I have a feeling that this has been scaled for a slightly different model. I think these numbers on this axis might be slightly incorrect. I think this might be for a slightly different version of the model. I'll have to check that afterwards. Regardless, the same qualitative picture is holding, right? So for low enough values of R, we just end up at one value. Oh, I know what's going on. It's fine. Monotonically stable for R less than 1. This is all fine. We can't actually tell on this diagram when it's oscillatory stable, but we know when R is between 1 and 2 that it's oscillatory stable. So in all of those cases, in the long term, what this diagram is doing is just plotting, simulating those time series, and then just plotting the values that we get after a long enough time. So here we just tend towards this carrying capacity, and we do it either monotonically or oscillatory. Then once we get to R above 2, we're now going back and forth between two different values. So here, this is oscillatory unstable. In fact, it's oscillatory unstable for all of these values. But between 2 and about, I don't know, 2.4, we have a 2 cycle. So it's going back and forth between just 2 values. This point here, and stop working. My screen stopped working. Let's try that again. I think it's because this is a very large image, which is why it doesn't like me zooming in on it. So I won't zoom in. At this point here, when R is 2, you're not letting me draw this. At R is equal to 2, I'll just point here instead. There we go. At R is equal to 2, we have a bifurcation. Okay, so the bi in bifurcation is telling us that we're splitting. This can describe, say, even as a tree grows, it bifurcates into 2 branches, it bifurcates into more branches. So that's where this bifurcation word comes from. So it bifurcates here, and we have these 2 outcomes. Then more bifurcations happen again up here when R is about 2.4 or so. Now we're going to do 4 different values. So this is now a 4 cycle. That doesn't last very long. I won't zoom in, but you can on your own computers if you want. Around about here, we end up at an 8 cycle, so going between 8 different values. See that each time we're only increasing R by a tiny little bit more, and the behavior is suddenly shifting. And then eventually we end up with chaos. So all of these values here, what it's saying is that after we simulate this for a long enough time, we just keep going between all of these values. Whereas here, we end up at some stable values or just oscillating between 2 or 4 or 8 values. Here, if you let it go for long enough, it will go across all the values. There's actually a little section in here where it stops being chaotic again, and then it starts being chaotic. So this slide here is just describing what I've been talking about just now. This key thing I'm going to focus on this idea of chaos. So what does it mean when we talk about something being chaotic? Has anyone, I think I asked this the other day, who's heard of chaos before in the context of maths, right? Or the butterfly effect. Okay, good. So chaos looks kind of random, but it's not random. That's the key thing. So we define it as being something deterministic. So when we're saying deterministic, it can be determined if you start with the same initial conditions, you'll always get the same output. So there's no randomness here. So it's completely determined by your initial conditions, but it's aperiodic. What do I mean by aperiodic? Just means there's no period. So a 2-cycle, there's a period, right? It goes back and forth, just like a sine wave has a period. 4-cycle, 8-cycle, they all have a period where you go back and forth between a certain number of values, and then you start back at the beginning of that cycle again. So there's a period to that. In chaotic dynamics, there's no period. That's why we call it aperiodic. It's also bounded. So although we're taking all of these different values, we're not going off to positive or negative infinity. Obviously, with a population, we can't go to negative infinity, but from a mathematical point of view, we say that it's unbounded, so it doesn't go to, sorry, it's bounded, so it doesn't go to either positive or negative infinity. And crucially, we have this sensitive dependence on initial conditions. So that means a very small perturbation can become large. And this is where this name coming from a famous quote. When people talk about chaos, they often talk about the butterfly effect. You've heard of the butterfly effect? Yes, okay. The idea here is that certain natural systems, here we're talking about populations, which can exhibit chaos, but also climate models and weather systems can be chaotic. The idea here is that a very small perturbation, for example, the flap of a butterfly's wings, when you feed that into your model, because it's such a small perturbation, eventually it can lead to something completely different on the other side of the world. So it could lead to a hurricane on the other side as well. That's where that quote comes from. It's a bit exaggerated in some sense, but weather dynamics are chaotic. So there's a reason why, you know, we can predict very well what the weather's going to be like this afternoon, tomorrow, in a couple of days' time. As soon as it starts getting sort of 5, 6, 7 days out, your measurements of the current state of the climate and things like temperature, humidity, pressure, they have to become more and more accurate because these small perturbations lead to wildly different outcomes. So that's why this is kind of cool. So I have a couple of questions for you guys. Maybe chat to the person next to you for a minute or two. I want you to think about what are the implications for chaotic dynamics for real populations or our models of them. So there's kind of there's a biological consequence for having chaotic dynamics, and then there's also a modeling consequence. So have a think about that for a minute or chat to the person next to you. Okay, I don't hear any chatting, so I hope there's just thinking going on. Who wants to tell me what a possible biological interpretation or consequence of chaotic dynamics might be?
Like explode we like follow a line and suddenly just go way up, go way down.
Exactly, yeah. So these are unstable oscillations by their very nature. We're not tending towards a particular point. So these unstable oscillations can lead to these population crashes or extinctions. We're not modeling species interactions here, but there's also a possibility that if the population suddenly explodes, like we said, then you might be taking away resources from other species in the environment. So the main issue, though, is this idea of population crashes and extinctions. This can happen when we have just ordinary unstable oscillations where we're going around and we're going between high values and low values. And although we don't have randomness in these models, obviously real populations have randomness. So if you go to a very low level, they might just stochastically go extinct. But when we have chaotic dynamics, because we're kind of going back and forth between all these different values, you again might just end up at a point where you happen to go extinct. How about from like a mathematical perspective, when we're trying to, we're trying to model, think about why we're trying to model populations, like why could this be an issue? Any ideas? Okay, let's take a step back and think, okay, what do we want to use our models for? Just as a general thing, you know, we do make a mathematical model. Why do we want to do that?
To make predictions.
Okay, yeah, so making predictions is one like obvious reason as to why we often use them. So why might chaos be problematic if we want to make predictions using our models?
Just make it unpredictable and future.
Yeah, so just like the weather, right? You know, we can only predict for a relatively short period if we have systems that exhibit chaotic dynamics. So, you know, if this was a population, we might be able to say, okay, we might be able to predict their population size over the next like 5 months or 5 years or whatever, depending on things like their generation time and population size and so on. But then we might say just beyond that, we don't really have any idea. So these chaotic dynamics can make it very difficult for us to say what's going to happen in the long term, or 10 years from now, because these small perturbations get amplified over time. Okay, so how do we say this? So our models only good for short-term predictions. Just to really emphasize this point, though, this isn't because of randomness. This is because of small differences in your measurements. So even when you go out and measure things, your measurements are never going to be completely accurate. So errors can come in from there. Small differences in those measurements or even in the assumptions that go into your model could cause massive downstream differences. This is a note. This is very different to, if I go back up to say one of these examples here, if you had a small difference in your measurements here, say what the actual current population size is, and then you try to project it forwards, you would still end up in these cases always at your carrying capacity. So even a small difference in your prediction doesn't lead to a big difference further down. And even this example here, where we had this cycle, if I had a small difference in my initial conditions, so suppose rather than here, I start along here instead, I would still end up with a cycle that looks kind of like this. It'd be a little bit different, but it'd be fairly close. So the difference between these non-chaotic dynamics and these ones down here is that these small perturbations don't make a big difference to your predictions in the long term. Right down here, right screen, if I end up with a small difference, rather than here, I start off here, my trajectory would end up looking completely different. So if my point here, I end up here, I might be all the way up here. Any questions about chaos? Yeah.
Are there any current real-world examples?
That's a very good example. And a very good question. Sorry, it's quite difficult to definitively say whether something is chaotic or not. Populations that have like annual cycles and have these, the very reason why we model these certain populations in discrete time is because there's a lot of seasonality. So you have to first of all look for ones that are highly seasonal. Things like insects and plants, they could often demonstrate these kinds of dynamics. I'm not aware of any ones that have definitively been shown to be chaos. Usually things are a bit more complicated and there are other things going on. They might be cycling like this and think, oh, is that chaos? But it might be because there's a predator involved or something like that. So these are kind of idealized, and they do tell us something about like the fundamental dynamics of populations, but it's kind of hard to definitively say this is an example of chaos in a real population. A good question. Okay, so back to bifurcation diagrams. So we want to summarize what's going on. And here, this was an example of a bifurcation diagram that was generated numerically. And we talked about chaos. So what are the different types of bifurcations that we might see? Well, we've seen one example here of something called a period doubling bifurcation. That's where we went from just this one value into 2 values, and then from 2 to 4, 4 to 8, and so on. So these are period doubling because the periods of our cycles are doubling. So that's one type of bifurcation that we can have. Usually it will look something on a numerical diagram, something like this, where each time we're doubling. So we're seeing these bifurcations like this. This isn't the only type of bifurcation though, and we're going to meet lots of different types during this course. Usually bifurcations are quite interesting because they're telling us about some sort of qualitative fundamental change in the dynamics of our system. Okay. So there's actually another type of bifurcation in this logistic growth model, and that occurs when R is equal to 0. So usually we've been saying R is greater than 0, so R is our intrinsic growth rate. Remember this R as well we defined to be the difference between the births and the density independent deaths. So usually we were saying, okay, we're going to fix this to be greater than 0, because if it's less than 0, then that means we've got deaths are always greater than births, and so the population just goes extinct. So it's kind of trivial and not very interesting. So usually we make this distinction here. But if we remove this distinction, we say, okay, we're going to allow these births to be potentially less than the density independent deaths. Then we actually see another type of bifurcation. This is called a transcritical bifurcation. And the key thing about a transcritical bifurcation is that we've got two steady states. And as you increase a parameter, you change a parameter, the stability of those states switches. Okay, so you start off with one, say this one up here being unstable and this one down here being stable. As you increase the parameter, they switch, so their stability changes. In this particular model here, the stability changes when R is equal to 0, because that's the point when our births equal our density independent deaths. When R is less than 0, our extinction, trivial steady state n star of 0 is going to be monotonically stable. In fact, we could see that if we were to sketch a quick cobweb diagram. So my NT and NT plus 1. We have a diagonal line here. If we have R being less than 0, the gradient here is going to be less than 1. So now we have a function that looks something like this. Doesn't matter what it's doing over there. Now if I pick any initial condition, say here, when I cobweb towards this extinction state here at 0. As you increase R above 0, this red curve will have a gradient greater than 1 at 0. Okay, so that's why this is monotonically stable when R is less than 0. It's monotonically unstable when R is greater than 0. So that means we have a transcritical bifurcation. So there's an exchange of stability. Okay. What I want you guys to do is to have a go at analyzing this model. So whenever possible, I'm going to try in class to get you guys to have a go at practicing examples. This is good to make sure that you've understood it. It also means I don't have to stand here just lecturing at you. You can actually do some math. I think it's a better way of learning. Also means I can come around and answer any questions. Gives good practice for things like exams as well, to make sure you really have understood how to solve them. So this is another type of discrete time population model. So this is from the 1950s, between a couple of mathematicians, Beverton-Holt. This is originally intended to model fisheries. So our N's here are referring to the number of fish in the population. And here they are assuming that the mortality rate is proportional to the population size. So they still have an intrinsic growth rate R here, but they also have a slightly different setup here, where we're dividing this intrinsic growth by a mortality term where A controls the strength of the relationship between population size and mortality rate. So there's a bit of a different setup here. We can't split this really into like births and deaths, but this is, you can see as n gets larger, the term on the bottom is going to get larger as well. So it's going to modify our growth rate. Okay, so the other day we looked at how to find steady states. and their stability. So I want you guys to, first of all, find what the steady states of these models of this model is. So remember, if this is my f of nt, steady states are when we have n star is equal to f of n star. And then stability, remember we want to take f prime and evaluate it at n star. And then look at whether this has magnitude greater than 1 or less than 1, and whether it's positive or negative. And that will tell you whether it's monotonic or oscillatory, stable or unstable. Okay, so that's the first part as practice. And then the next thing we're going to do is sketch a bifurcation diagram. So I'll let you guys work through the first part for the next 5 or 10 minutes or so, and then we'll come back and sketch the bifurcation diagram. Okay? Does anyone not know what they're doing? Okay, I'll come around and help. Okay, I can see this one's causing a few problems, so I will work through it with you guys. This one is definitely a little bit harder to analyze than the logistic model, especially when we come to the stability. Okay, so the first thing, the steady states, what do they look like? Okay, remember our steady states are just going to be values of n, which I'll call n star, where we have the left-hand side being equal to the right-hand side. N star is equal to Rn star over 1 plus An star. So that's just setting the left-hand side and the right-hand side equal to each other. What does this tell me? Well, I could either have N star being equal to 0, then both sides will be balanced. We'll have 0 is equal to 0 over 1 plus 0, so that's all 0. Or I can divide throughout by n, or n star. If I divide throughout by n, I have 1 on the left-hand side, r on the right-hand side, and 1 plus an star on the denominator still. So now I can rearrange. If I multiply both sides by 1 plus an star, and that's going to equal r. I can then subtract 1 from both sides. An star is equal to r minus 1. And then divide by a, because a is non-zero. So n star is equal to r minus 1 over a. So this tells me I've got two steady states. I'm not quite finished yet, though. Key thing at this point, we need to say, when is this biologically realistic? I've got a trivial steady state, which is always n star is equal to 0. That's always biologically realistic. Doesn't matter what my parameters are, that always exists. This n star is equal to r minus 1 over a. When is this biologically realistic? So yeah, a's got to be greater than 0. Anything else? So when we're saying biologically realistic, we're basically saying this has to be positive. So r has to be greater than 1. Yeah. So we need a to be positive. Usually this is within. In fact, I don't know if this was in. This should have been in the question, really. This should have said a is greater than 0 here. So that was kind of taken as a given, but crucially, r has to be greater than 1. That's the key one. Okay, so we've got two steady states. Whenever you're finding steady states, or equilibria later in the model, whatever you're doing, always think about when is it biologically realistic. Okay, mathematically, this is a steady state for all values of r and non-zero values of a, but it's only biologically realistic when n star is positive. Okay, so now we need to think about the stability. Recall our growth function, f of n is equal to Rn over 1 plus an. To find our stability, we need to take the derivative of this with respect to n. So here we're going to need to use the quotient rule. I'll just abbreviate to the quotient rule, QR. So f prime of n is going to equal, take the derivative of what we have. Let's see, just make sure I've done this correctly. Yeah, this should be right, I think. So we take our derivative of the thing on the top. We have r times by 1 plus an minus what we have on the top, rn times by the derivative of what we have on the bottom. So the derivative of that with respect to n is just going to be a. And then we divide by our denominator squared. So we can expand the numerator out. We're going to have an r plus ran minus ran. So this is going to cancel with this. We'll just be left with r over 1 plus an squared. So we found the derivative of our growth function. And then that's for a general value of n. We now need to think about what happens at our steady states. So let's think about n star is equal to 0. Our f prime at 0 is going to be r over 1 plus 0 squared. This is just r. That means that if r is between 0 and 1, our trivial extinction equilibrium is going to be monotonically stable. And if r is greater than 1, this is going to be monotonically unstable. This will become clearer, by the way, when you look back at the notes. There were several conditions as to, depending on the values of this, what is the stability at this point? Okay. Yeah.
We need to apply the biological realistic to that time equals 0.
Not for this case here, because this is a good question, because we'll come back to that in a moment. This is true for all values. So it doesn't matter what the values of r are. This is always biologically realistic. So it's always biologically realistic for the population to be extinct, essentially. But hold that thought, because we'll come back to that in just a second. So now we need to look at the other point. So n star is equal to r minus 1 over a. So it's a little bit more tricky. So we have r minus 1 over a. Get the gradient of our growth function. So what's this going to look like? Well, we're going to have, let's see, we just have r on the numerator, and we have on the bottom 1 plus a times by r minus 1 over a. So the a's are going to cancel. So we're going to have 1 plus r minus 1. Got a plus 1 and a minus 1. So we're just going to end up with r over r, which is going to equal, oh, sorry, this is squared on the bottom. I think someone was just about to correct me, I think. We have r over r squared, so we're going to have 1 over r. Okay, so again, let's think about values of r. If r is between 0 and 1, then our gradient is going to be greater than 1. So this is going to be monotonically unstable. And if r is greater than 1, it's going to be monotonically stable, because 1 over r is going to be less than 1, but still positive. Okay, so what do we notice here? When r is less than 1, one at the top is monotonically unstable. And this one here is monotonically unstable. And then as we pass through 1, when r is equal to 1, we now have that our trivial equilibrium is monotonically unstable, and our carrying capacity is monotonically stable. So they switch stabilities, right? So we can summarize this in a bifurcation diagram. And what does that look like? Now, if you recall, in the bifurcation diagram, what we have is our population size, our steady states on the vertical axis. And then along the horizontal axis, we have a parameter that we're varying. It causes a change in the steady state. So what parameter is going to go? We've got two parameters in here, A and R. What parameter am I going to put on my horizontal axis? R, right? Because A doesn't have any effect on stability here. It's just R. So R is the one that we're interested in. Okay. What is the key point at which we have a bifurcation here? R equals 1. Okay, yeah. So R is equal to 1. That's going to be a key point. And what do we have? Well, let's think about our trivial steady state first. I'll draw this in red. So our trivial steady state is just going to be n star is equal to 0. And we have that when R is between 0 and 1, it's just a solid line here, I've drawn in red, this is stable. But then when R is greater than 1, this becomes unstable. So we usually denote stability on these diagrams by a solid line and instability by a dashed line. So we have a key here, solid means stable, dashed means unstable. Okay. We need to sketch on our other steady state as well. So what's our other steady state? So other steady state is this up here. N star is equal to R minus 1 over A. So what does that look like? Well, we've got a graph here of N versus R. So what does N is equal to R minus 1 over A look like? As R varies. Is this linear? Is it quadratic? Is it something else? It's just one. Exactly, yeah. So if it helps, we can write this as 1 over A times by R minus 1 over A. This is our intercept. And this is our gradient. Okay, so it's just the equation of a straight line. A is positive here. So that means that we're going to be intercepting for some minus 1 over A is going to be somewhere down here. And we're going to have a slope, let's say looks something like, so we know that when R is greater than 1, our carrying capacity is stable. So this is why this is a solid line. We don't have to sketch this in, but just for clarity, this line continues on. Not biologically realistic for values of R less than 1, remember, but mathematically it is unstable. Okay, so if we could allow any values possible, it would look like this. So note that we've got a change in stability, that we have this line here changes stability as we go through R is equal to 1. And this line here, again, changes stability, but in the opposite direction as we go through R is equal to 1. So what can we say? We can say that there is a transcritical bifurcation at R is equal to 1. It's a transcritical bifurcation because we have two steady states. Mathematically, they exist all the way along this domain. Their stability is switching, though, at a particular point. And that point corresponds to when the births are greater than the density-independent deaths. So essentially, our population becomes viable. Think about a biological interpretation of this. Here, our population is unviable, just goes extinct. And on this side of the dashed line, our population is viable. And so as long as we have any positive number of individuals in our population, if we started off, say, here, we would go down. The population would be driven extinct because the population is not viable. If we started at the same point here on this side, our births are greater than our deaths. So the population is viable and we would go up to our steady state. Okay. Any questions about this diagram or about any of the analysis I did? Yes, Scott.
Sorry, so what do you mean by like unviable and viable? Just that the population starting on.
Yes, when I say the population is unviable, I mean that it can't survive, it goes extinct. There's no population size for which it can survive. It always just gets driven extinct. When I mean it's viable, I mean that there is a stable, steady state here, or at least it's not driven extinct. So here it's extinct, there it's not extinct. Any other questions? Okay, the self-study problem is another Jupyter workbook. To get you guys familiar to using Python to try to numerically understand what goes on in some of these models. So the Ricker model was introduced, I believe, at the end of the last lecture. Try using that workbook to plot a bifurcation diagram. So there's tools in there to help that. That also, if you don't understand that one, it might be a good one to bring along to the tutorials as well. Okay, that is it for today. Have a good weekend. Next week, we are going to be moving on to continuous time models. So we'll be leaving these discrete models behind, thinking about what happens in analogous continuous time models, and then starting to think about things like overfishing and harvesting populations, and also pests and how we can potentially control them. Okay, have a good weekend.